Hello, I'm Philip Patrick, a fourth and final year student from Faculty of Manufacturing Engineering, taking this semester Bachelor Degree Project 2 for this semester. So I'm going to present my FYP regarding the effects of stirring time on the rheocast microstructure and the mechanical properties of magnesium alloy. So here is my table of content. I will explain it further. So for my problem statements is magnesium alloy are very reactive to temperature change, and second one is magnesium alloy has poor formability in room temperature. And for my objective and scopes, for my first objective is to study the microstructure of magnesium alloy feedstock and to investigate the mechanical properties of magnesium alloy feedstock, and lastly is to determine the influence of stirring rate and stirring speed of magnesium alloy feedstock. So for my scopes, it covers on the effect of stirring time and stirring speed of magnesium alloy AM50, and it focuses on the microstructure analysis of the feedstock samples and determine the mechanical properties through mechanical testing. So here is my flowchart of study. I will explain it further in detail. So for my design of experiment or DOE, so the method that is chosen is Taguchi method. The parameters selected are based on past journals, and it is selected to determine the optimized parameters, and it is designed with two factorials with 4 levels, and it has a total runs of 16. So my parameters is stirring speed and stirring time. For material preparation, so the chosen material is magnesium AM50. So the ingots are prepared to obtain 16 samples according to Taguchi method, and each cut materials are weighted at 200 gram for each sample. So the ingots are cut using the bandsaw machine. So after the raw materials are cut, now we proceed to feedstock preparation or rheocasting. So first is the furnace is heated up to 650 degrees Celsius, and the raw materials were inserted and melted. So once the raw material is melted, it will be cooled down up to 610 degrees Celsius. The stirring started following the design of experiment, starting from the run number 1, and the steps are repeated to obtain the remaining samples. So lastly, we will gotten 16 samples out of from rheocasting. So next will be done for polishing and etching. It will be used from a hardness test and microstructure analysis. For first, it will grind for 200, 400, 600, 800, and 1100 grit. Then it will be polished with diamond PC, polycrystalline suspension, from 6 micron up to 1 micron. Then the samples were etched for 10 seconds in an etchant or specifically callus region. So after it were etched, we proceed to microstructure analysis starting from optical microscope. So for hardness and tensile test, the hardness and tensile test is done according to ASTM E92, and the tensile testing is done according to ASTM E8M. The gauge length for tensile testing ASTM E8M is 20 mm, and 4 mm of radius is selected to perform the tensile test. So next we'll proceed with the result indication. For Taguchi analysis on the hardness, from the graph we can see that the stirring speed has positive influence the hardness test the most. It ranked the first among the two. Then it will closely followed by the stirring time. The high speed tends to disintegrate the dendrite's arm, thus it tends to influence the hardness of the magnesium alloy. So from the graph you can see that the stirring speed has a very high mean of means compared to stirring time, and from the response table it shows that the stirring speed, the rank is first, then followed by stirring time number 2. Then for Taguchi analysis for tensile strength, the stirring speed once again had positively influenced the tensile the most. It ranks first among the two. Then the fragmentation of dendrite arms enhanced the mechanical properties of alloy, uh, specifically the hardness and mechanical tensile strength. So once again you can see that from the graph it shows that the stirring speed plays a crucial role in influencing the tensile tests. So next is microstructure analysis for optical microscope. The rosette primary particles was observed after the stir casting or rheocasting in semi-stat slurry. For the raw material of magnesium alloy, it shows in dendrite type primary particles, but after it undergoes rheocasting, there is no dendritic matrix particle is found. And from the OM, we can see that there are less porosity and lesser grab due to the fragmentation of dendritic arms. So under the 200 magnificent, you can see that there is no longer dendritic arms or dendritic presence in the microstructure. From here, we can see that after going through the stirring time or stirring rate, it shows that the disintegration of arms, of dendrite arms, is no longer be found, and the rosette particles is found. Okay, for scanning electron microscopy or SEM, there are three intermetallic phases found in SEM image. Then the needle tape shaped particles is observed. Then after going to a higher stirring rate or higher stirring time, there is no longer presence of B, magnesium aluminide, and alpha magnesium after an increase of stirring speed. So from the first image, you can see that there is a mixture, there is a combination of beta magnesium aluminide plus primary magnesium, and you can see that there is presence of B phase of magnesium aluminide and a needle shape particles. For the needle shape particles, it influences or it affects the mechanical properties of magnesium alloy. So for X-ray diffraction, you can see that the A phase of magnesium alloy has a very high volume compared to the three phases. So previously from the SEM, we observe that there are three intermetallic phases that occurred in X-ray diffraction. So in SEM, so in X-ray, we can confirm that magnesium aluminide, magnesium manganese, and magnesium were identified and verified after X-ray analysis. So for hardness testing, after we have done the hardness testing following the STM per guide E92, from the table it shows that run number 16 recorded the highest value among all. So according to mechanical properties of magnesium alloy AM50, the hardness value of magnesium alloy AM50 is 60 HV, because however we recorded 100.7 HV after going to rheocasting, and it shows an improvement of 66.67% of improvement. This can be due to what I have mentioned just now from the microstructure analysis. The fragmentation of dendritic arms shows that the rosette primary particles that occur that were formed in the microstructure, thus it shows that it has less porosity on cavity, then the spaces among the particles is quite less, so it is closely bonded to each other, thus the hardness value increase. So from the highest value started from run 16, followed by run 15, and followed by run number 12. We can see that from here, based on the Taguchi method, it shows that higher speed tends to influence the result of the mechanical properties. Then for the tensile testing, once again, the run sample number 16 recorded the highest value among three types of strength. First is the tensile strength, the ultimate tensile strength, and the elongation at break, and closely followed by run sample number 15 and sample number 12. Ultimate tensile testing, it shows that sample 16 recorded of 251 MPa, and the yield strength is recorded of 131.05 megapascal, and elongation at break it shows an increase of 20.32% from sample 16. So to conclude, we can see that the yield strength it increased from 124 megapascal to 1310.5 megapascal, and the ultimate tensile strength it improved within 5%, and the elongation it increased by 3%. So we see that how much the influence of stirring rate and stirring time affect the mechanical properties of magnesium alloy. So to conclude, for the first objective, study the microstructure of magnesium alloy feedstock. The output we can get is the higher stirring speed and longer stirring time have uniform size distribution of primary particles due to little formation of larger cluster. And the intermetallic compounds were detected in microstructures and were observed by SEM and identified by XRD. The intermetallic compounds have dissolved into a alpha phase of magnesium during high stirring speed. And the second objective, the output is the hardness of magnesium alloy was significantly improved by 60.67% with value of 100.7 HP. The yield strength of alloy increased from 124 MPa to 131 megapascal, while the UTS strength exhibit an improvement of 5% and increase of 251 megapascal, and the elongation to break had substantial growth from 15% to 80%. And lastly, to determine the influence of stirring time and stirring speed of magnesium alloy feedstock, the stirring time of 8 minutes and stirring speed of 600 rpm is optimal during casting to transform the dendritic alloy into a more refined dendritic solid particle, which is from the sample 16 or run number 16. So for recommendation, for the first recommendation is to lowering the cooling temperature a bit more. So the initial cooling temperature for this study is 600 Celsius, and the proposing of cooling temperature below 600 degrees Celsius might affect the microstructure and mechanical properties a bit more. So from the result of tensile and hardness test, so higher stirring speed and longer stirring time as achieved from this study, this alloy microstructure and mechanical properties increase significantly. And lastly is to minimize the size of cylindrical stainless steel mold die. It took a long time to produce and it produced scrap. Thus, reducing the size of die will help to reduce the time for material removal and reduce the scrap, while we save the environment. So that's all from me. Thank you.